next up, we have a keynote address by Dr. Bharadwaj from Artpark. He'd be speaking about infrastructure, aided autonomy, and wireless edge compute for robot operations. Can we have a round of applause, please? Thank you. Thank you.
Thank you, Pallavi, and good to see that most of you are awake. I hope you'll stay awake after half an hour. So, I want to basically talk about how typically when we are when we have been when you're engineering robotic solutions, it's usually a solution around a single robot. Of course, people are talking about swarms and so on, but it's not yet there. The thing is that unlike humans, machines and robots can come with connectivity, and connectivity technology is also very advancing pretty fast. So what that means is that you can do things, you can think about solving problems in a different way, right? You can break up a problem to be solved across multiple entities working together, right, in a collaborative or cooperative fashion. And so I'm pretty excited by this possibility. We have just scratched the surface in ISC Artpark. So I'll just tell you a little bit about what we are trying to do. But hopefully, if you're not thinking along these lines, it will inspire you and you might do more stuff, right? So if you take any mobile robot, the compute is going to be limited thanks to size and more importantly, energy considerations, right? And yes, we have NVIDIA giving JetSense and so on, but no matter what, you would like to kind of keep the compute in the robot as small as possible. So the robots have small brains with them, right? But then if the robots have access to a good wireless technology, I'm talking about mobile robots, so you need wireless, right? And if that wireless connectivity is very high quality and low latency, then you might as well, do some of the compute in the edge cloud, right? And the word edge is a little bit confusing. Some people, what the robot is called the edge. For some people, the next hop is called the edge. So I'm just going to use that terminology out here, right? And you can get a little bit more compute. For example, it could be your house, right? Or it could be your factory, your office, where you have some servers and which are a little bit more compute than what is available on the mobile robot. And if you have a good connectivity, very low latency, you can actually do stuff from the edge cloud. And then, of course, you have the public internet, and you have Amazon, AWS, Robotics Cloud, or Azure Cloud, or whatever, and you can do more heavy-duty stuff there. So we have this hierarchy available to us. So when we are designing solutions, and some of you are already doing that, I see that. But when you can also have handle on the latency, you can actually think of how to partition your solution across these three different layers. And I see that ROS2 and some of the advances are already enabling you to actually do this kind of solution development on top of ROS2, where security and you can do away with VPN is what was mentioned in the morning. So all those are really great kind of infrastructure support for enabling this kind of distributed solution to emerge. On the other hand, if you look at AI itself, right, how is AI developing, right? The so-called, again, the first generation of AI about 10 years back was all around inference, right? You give you create this AI model, you give an image, you ask a question, and you get an answer out, right? What is happening now is really solutions which are beyond just answering a question, right? So these are solutions where some thinking is happening, reasoning is happening, right? A chain of thought, search, long horizon planning, those kinds of things, like what humans do, right? We kind of do it that way, and AI is also moving in that direction. And the future will be where you have teams of AI agents working together, right? Already we hear of agentic AI, and we'll have teams of AI agents working together, better than humans. And for humans, we communicate through language, and it's a slow time scale. Whereas robots and AI agents using communication technology will be almost instantaneously talking to each other, right? So it again changes the scope. I mean, it's scary, but at the same time, it can enable lots of interesting things. So this is the other perspective of how AI itself can benefit from this hierarchy of compute capability with connectivity in it. And the AI systems which are there, right? So they are actually, kind of going towards, as I said, in the beginning it was inferencing, and then inferencing with more factual information through databases and so on, with planning brought in. And as we go forward, I do believe that, if you look at ChatGPT, it is using information which is maybe a month old or 2 months old or whatever, right? Because it's trained on huge corpus of information. But you want to be able to kind of do reasoning and planning using real-time information. And that's where digital twinning technology also becomes really critical, right? So you have archival data, digital twin data, and then you're basically you're building solutions based on that. So this is kind of the broad framework which I see happening with connectivity and AI. And essentially, we are trying to develop solutions using these two kind of pillars in some sense, right? And so today, what I'll talk about is two kind of specific problems we have been working on. And as I said, there's lots to be done. So it's just, I feel it's just scratching the kind of the surface in some sense. One is how we can actually use the collective information available in the infrastructure for robotic applications. So in this specific example case I'll take is just navigation, localization leading to navigation, right? But there are other things also you can imagine as you go forward. And the second aspect is it kind of evolves from here is a broader concept of this digital twin, which I mentioned, but which is also kind of accurate to the 3D world and brings in semantics and so on. So hopefully it will enable robots to operate in a much more interesting and rich way. Right? So, if you take a typical robot, a mobile robot, right? You have sensors like IMUs, etc., and then you have your SLAM algorithm, which is part of your nav stack, and they work by themselves in isolation in some sense, right? And EKF refers to the algorithm used to actually fuse information from multiple sensors, and typically it's done within the robot itself, sensors within the robot, right? But now imagine that this robot is able to tap into, we have also typically in many of the industrial settings, you'll have cameras, CCTV cameras, for example, and then you also have a communication network. And now, people already, the private 5G networks are starting to get deployed. In the West, it's already, people have been adopting it. The reason I mentioned private 5G is that you can now have a wireless network with good connectivity, high quality of service, low latency, and so on, right? As opposed to a public, kind of Wi-Fi type infrastructure where you don't have control over the quality of connections, right? So it becomes difficult to develop industry, kind of scale solutions. Whereas with private 5G, you will be able to do those solutions going forward, right? So now imagine you have this kind of a private 5G network, and you have now sensors which are fixed in the infrastructure, as well as sensors which are there in other robots, right? So that is what I meant by collaboration, right? And so now can we actually fuse all this information in real time and help any particular robot do whatever it's supposed to do better, in this case, to know where it is, right? And then also eventually plan its path. So that is what we basically, this figure is kind of illustrating how you need to have this middle block in between, which is figuring out how to fuse all the information coming from all these different streams, and then extracting something relevant which can be given to the individual robot, right? And so what, in this case, we want to extract is being able to see where the robot is, extract its pose, And typically, when you kind of get information from a sensor, you would also like to know the uncertainty associated with that measurement, right? That is what is called covariance. So that becomes important to be able to fuse information from multiple sources so that you can weight it according to the kind of uncertainty which is there with each information source. So, and of course, all of this can be built on ROS, and ROS nodes are there which can kind of, which provide the underlying middleware to actually handle all this. So, but I'm going to kind of focus more on some of the algorithms which are being used to kind of do this, right? And there are certain other things out here. The multi-view fusion involves detection, tracking, association across multiple cameras, and so on. I'm not going to go into all of that due to lack of time, but I'll just kind of touch upon one or two things. So one is, how to estimate the pose of something which is outside, with the camera. And so one of the approaches which actually works well, but I'll tell you there is a drawback with this approach, is to actually start with a 3D CAD model, right? So this is one of the robots we have, and there is a 3D CAD model you can build, and that CAD model is accurate in terms of the sizing and so on. And once you have the model, you can identify certain interesting points on that robot, right? These are points which a camera can and the algorithms can pick up, right? Corners, lines, whatever it is, right? And you manually annotate it. And then what you do is that your goal is that when I see that robot from a camera, I had to automatically figure out, what are the important key points, and where they are and so on, right? And then using that information, you can actually figure out the pose of the robot. Now to do that, you train a neural network, and the way you train it is by, you need lots of data, and then, you can actually generate the data synthetically, as was mentioned earlier in the NVIDIA talk. You can synthetically generate data which is the rendering of this robot in different poses, in different backgrounds, different lighting conditions, etc. Right? So what is called domain randomization, so that you have huge amounts of data, and when you train a neural network with lots of data, then maybe you overfit it, but you actually, if your actual real world data is within that distribution, you get very good performance of your network, right? So once the network is trained, and the network, you can take any vision based network. Here we have used YOLO, and you can train that. And now when it sees, after it's trained, when you deploy it, when it sees an actual image for a robot, it is able to kind of extract all the interesting points, right? Because when you trained it, you said, okay, these are the interesting points on the robot. So it's able to extract that. And once you have that, then standard, computer vision algorithm, what is called ransack PNP, can be used to extract the 60 pose. Now, the thing is, when the drawback of this, okay, I don't know how to go back. I'll tell you what results you get. Actually, you get very good results, centimeter level accuracy, and very good yaw prediction and so on. But the challenge is that I need to create this CAD model, and I went back. Okay. I need to create the CAD model and so on. But what if I want to kind of extract the pose of a human, right? No one is going to, if I'm in a factory and a person is walking around, I would like to know where the person is, right? I can't create a CAD model for that. Or there are certain passive objects, like maybe tables, chairs, which also get moved around. But again, I want invest time in creating CAD models for that. So can you come up with a solution which can work without, kind of creating CAD models like that, right? And so one of the approaches is the same concept of having something in 3D and then having something in 2D and matching it, right? But what the one in 3D is created through what is called structure from motion, right? So you can take an object, you can walk around it with a camera, and you collect a video, and then using that, the computer vision tools called, so this concept of structure from motion can be done to actually create a 3D model of that object. And again, I won't go into too many details of some of the things out here, but here, instead of using YOLO, which we trained, it turns out that now foundation models have advanced so much that we can directly use them. So using a few foundation models like SAM, segment anything, and alike is something which automatically detects key points. You can now take an image. Sorry, you can take an image and go back. Yeah. You can extract, pass it through these models. Now you don't need to do training of those models because those models are, largely they work well. And then you can actually also extract the 3D kind of, you can take a monocular camera and extract a 3D representation of the object. It's kind of okay to a certain extent, and for this application it works well. And then from there you can now kind of run your Ransack PNP and get the localization of the robot. Now you see there is a lot of computation involved out here, and doing this kind of thing in the edge, in the robot itself will be too heavy, and that's where the connectivity with the cloud kind of becomes very interesting, right? So this is an example where we have a robot. It's a small robot, and then these are some of the key points which are extracted as the robot is moving around. You see these red dots; those are the specific key points which are used to kind of do the matching, and then eventually figure out what is the orientation of the robot. There's a big table out here, but I think the important point in this table, if this is what is shown on the rightmost column, is X, Y, and Z, the angle. We are just looking in this example only in the 2D case. And these are the errors, so it's like a error of about 1 centimeter in X and Y. And what is shown on the left side is different ways of extracting the pose of the robot, right? For example, if you take the wheel encoder, which are kind of not very accurate to kind of know where the robot is, like the error is 4.8 centimeters, right? So that is a lot of error. Whereas if you just use a onboard LiDAR, right, you get down to 1.8 centimeters. Whereas when you start fusing information, whether it's a LiDAR with the information from a single camera, LiDAR from 2 cameras, etc., and even without LiDAR. So if you see the third row from the bottom, there is no LiDAR, and you can get to less than 1 centimeter accuracy. So you can do away with LiDARs actually, and basically use cameras to do your localization. So just another kind of, so besides knowing where my robot is, if I can also understand the scene, right? So just kind of for 2 very simple scenarios, just to kind of show you what is possible, right? So in this scenario, what happens is that this robot has a LiDAR, but the LiDAR cannot see the floor, especially objects very close to it. So you see all these objects strewn around out here, and so this robot on the left side is just navigating by its own, self, right? It's just using the data from itself, and it goes and hits things because it's not able to see below its foot, right? But because we have this camera which is looking at this, now you can actually, kind of do a estimate of the state of the world and pass it on to the robot. And then the robot is able to kind of navigate itself. So it's kind of not only getting a better sense of where it is based on the fusion of localization, as well as better sense for what the environment looks like. So just a simple example of how infrastructure and information from outside can help you do a better job. And in some sense, it's not new, right? We already use Google Maps, right? That's what we are doing. Infrastructure information is used by us to make our own trip planning. So we can do that for robots also. But we can do more, and this is kind of where we are going towards digital twin, right? Instead of just targeting a single application like localization and navigation, can we create a much more general representation of the world around us and enable multiple downstream applications, right? So that is what we are saying out here, is that I'm showing cameras on the left side because those are, I think, the hardest to work with. But you can overlay it with sensor data, telemetry data from, maybe you have machines and you have telemetry and all that can also be brought in. You fuse that and you create, now the yellow box is saying it's the digital twin, but overlaid with semantics, right? And the semantics is interesting because now you can actually build systems with which you can interact at a higher level with natural language. You can bring in common sense reasoning. You can do a lot of interesting things. But the goal here is to actually enable multiple such applications to emerge. Navigation we discussed, but you can do decision support, you can do what if analysis, you can do safety alerts, and so on, AR, VR walkthrough, you can do multiple things, right? So we are very interested in also having a visually accurate representation of the world around us. I think it can enable more interesting downstream application. as opposed to a digital twin, which was discussed about 10 years back, which was largely about telemetry and keeping state of machines. We want to also know how things look, right? You should be ideally be able to create a digital twin of this whole place, and which is visually accurate. And there are multiple technologies around it, but one very exciting technology which has emerged over the last few years is this concept of 3D Gaussian splatting, right? Typically, when you take a LiDAR scan or a RGBD depth camera image, you have what is called a point cloud. Every point or a voxel has certain location, XYZ location, and if it is from a camera, you also have a color, right? So in some sense, the 3D Gaussian splats are generalizing that representation. Instead of a point, there is a little Gaussian balloon, you can think of it. And the Gaussian balloon will have a certain shape and orientation. That is why they are like an oval shape out here, and they are 3D, okay? And each Gaussian bubble has a certain color and transparency associated with it. And one of the key things here is that, so you create this now, instead of a point cloud, you create a Gaussian cloud using the data which you observe. And these Gaussian clouds can be rendered very fast on a GPU. And then you can actually, it makes, now you can have a representation where you have less number of points than in a point cloud. So this potentially can scale to much bigger scenes because you are using Gaussian bubbles which are bigger than a point. But you get very good, high fidelity representation, visually high fidelity representation. And you can actually also do a lot of interesting things like editing. You can capture dynamic scenes and so on and so forth, right? So, for example, out here, why this is kind of interesting is that when you have a 3D representation of the world, you can do things which you couldn't do in 2D. So, for example, out here, in the central figure, there is a little toy cat, right? And you want to see that cat, but you see, we have zoomed in and you can't see the cat fully, that white thing out here, it's occluded, right? So if you try to say, where is the toy cat to a 2D model, it will fail because it's not seeing the cat. But if you had a 3D representation of that world, right? Maybe some other view you had in the past collected that image. So now you have to put it in your memory, right? That is the 3D semantic digital twin. So when you say, where is the cat, you can actually figure that out, right? Where it is, even though in your current view it is occluded. So that is basically the power of 3D out here. And just as an example out here, so what is seen out here is on the left side, the robot has seen this table in a lab, and then it has created the 3D representation. And here, unfortunately, I have to show it in 2D out here. And the robot has moved to a new place. And there the robot is just seeing the laptop, right? Now you say the robot, hey, get me that physics textbook, right? You can interact with the robot. If I had my representation out on the left side, where I not only have a visually accurate representation, but I also have the semantics that, okay, that is a book of physics by authors Resnick and Halliday, right? I can now actually have my robot, figure out what to do, how to go to that place, and so on and so forth. So that is basically where we are going towards in terms of enhancing the representation with semantics, right? So how to do that? How to actually bring in semantics out here, right? And so what I'm showing out here is again, I won't go into the details of how we create the semantics out here, but this is a 3D scene. You have a bunch of images, and then using those images, let me see if I can play that again. There is a 3D rendering of the scene. I mean, it's a rendering of a 2D rendering of a 3D scene when there are multiple objects out here, and here we are segmenting out only a specific object, which is the table, right? And then once you segment that out, you can actually edit it. You can remove the table from the scene and play it and so on. And, just to kind of illustrate what you can do, once I have my 3D representation, especially capturing dynamic scenes, things are moving around, you can edit the scenes dynamically. You can overlay it with semantics, and so you can do semantic-based interaction and so on. So I think it's a very exciting kind of, I would say, opportunity out here to build robots which will interact with the world, and our interaction with robots can be kind of abstracted to a higher level of interface. So And that is possible because of course, the compute which you can take advantage of, which is not on the robot, right? And that's because of the wireless connectivity. And the thing with this is that you can amortize the cost, right? You can have many robots which are low cost, but then you invest in your infrastructure around it. It's like street lights, right? You invest in street lights, it benefits a whole community out here. So you invest in your infrastructure with sensors, connectivity, and compute, and then you can enable many robots to actually take advantage of it. And you can also build new solutions where robots interact and collaborate with each other, right? And as I said, I think it's still very early stages for this kind of solutions to emerge. And a lot of opportunities, of course, for academics, from a research perspective, but also for innovators to create new solutions. And one of the things is that with AI-based solutions, and there will be a lot of AI-based solutions needed, you need a lot of data. And we have been also discussing with some of the people out here during lunch break how we really need to kind of create this data sets for physical AI, right? So we heard about physical intelligence in the morning. We need data, right? If we have data, we'll crack the physical AI problem. And that is where, as a community, we can look to see how we can come together to start creating these data sets for physical intelligence. So with that, I come to the end. So thank you very much for your attention. And I also thank all the collaborators out here.
So we have time for a quick question, just one.
Hello, Professor. This was an interesting presentation. I got some interesting insights. So I'm Udayanan, basically. I'm a research fellow at DRDO. So we were working on this edge-based drones and things like that. So we wanted to implement some basic visual odometry algorithms in the drones. So here because we cannot do dense slam or even sparse slam in the nano drones. But I want to know whether, you were saying that in spatial AI, we want to know where semantically segment everything. So I basically want to know whether we have to do accurate mapping of the environment. So in future, how it will go? Let's say I want to pick up a cup. Should I have all the dimensions of the cup in the hand? Is it necessary actually? Because it's so heavy to store. Even let's say if it is not. If in case of wireless, it is okay to have off-board computation to have everything. But even if we have a wireless communication, dumping all of the data individual CAD. If we have a CAD model the representation of absolute cup, the entire cup with so accurate dimensions, is it necessary actually?
Yeah. So in terms of the manipulation of the physical manipulation, I didn't kind of talk about that, right? But there is what is called the concept of affordances, right? You can, when I want to interact with a particular object, like for example, this mic, I want to push it up, this is the place at which I hold, right? At certain places are more favored versus others. So in some sense, if I know that, for every object, if I want to interact with the object physically, right? What is the way to interact? What are called affordances? Those have to be represented. Somehow the robot has to have that knowledge, right? I mean, we have to have that knowledge, but that knowledge you can actually embed as part of the semantic digital twin, what are called the affordances. But having those affordances, you still need to come up with a plan to kind of get the actual motion of the arm, the fingers, gripping, etc. Now, where should this data be, right? So that is one of your key questions, right? And if you had, you have to kind of work with the resources you have. I mean, if you are in a place where you just have a robot and you don't have anything else, and if you are working with only specific types of objects, you know that it's a factory and these are the only kind of things, then you can actually create solutions which will fit in that small embedded platform, right? I mean, hopefully the embedded platform is a little big than just a simple microcontroller, but that is where the kind of optimizing your neural nets, because you still need, I think, you will need deep learning based approaches to solve this problem, because it's kind of too complex to come up with a kind of a rule based approach. But you will have to optimize for those robots, put it in the edge, in the embedded, but it will be limited to only those. Right? But if you want to have a general solution, which can, like what we are generalists, right? We can do anything. Then you really need that compute and the data storage. And for us, in our brains, we are able to store huge amounts of data. Now, if you can get that level of energy efficiency in your hardware, you can still do it in the, your robot can be unconnected, right? And still do stuff. But, you need that data. I don't think there is a way around it if you want to have a general solution. Yeah.
Thank you. So one more question. So there was a recent developments like in sensor space also, like onboard within sensor itself computing the key points and things like that. What do you think about that? Like what is how it is evolving in India or like in our country and all?
I don't have an answer to how it's evolving in India, but certainly the thing is the following, right? If I compute right next to the sensors, then I can reduce the amount of data I transfer, right? And which is good, that can eventually lead to, like, if I know exactly what I want, that is what I should do. But if I don't know what I want, then you might want to take the raw data out, and then maybe you have a better way later on. You can come up with a better way of doing things, right? So it's always a trade-off. But if once you're sure this is what it is, then you want to optimize the solution by like instead of sending the whole image, you just extract the key points and send it, right? So you reduce. But then you need to have that compute in the camera, which many camera vendors are now starting to put, right? So you can do it that way, yeah.
So thank you, Professor Bharadwaj. If you have any other questions, you can directly talk to sir. Unfortunately, we are already running late with the agenda, so we'll continue with the next talk.
Thank you.
Thank you, sir. So the next talk is on ROS2 control with CANopen and J1939, leveraging automotive protocols for robotics by Anish Darvi from TCS.